Clear ആണോ? Okay. So നമ്മൾ നെക്സ്റ്റ് നോക്കാൻ പോകുന്നത് നെക്സ്റ്റ് ടൈപ്പ് ഓഫ് ഡൈവേഴ്സിറ്റി ആണ്. നമ്മൾ ലാസ്റ്റ് ക്ലാസ്സിൽ നമ്മൾ ഫ്രീക്വൻസി ഡൈവേഴ്സിറ്റി പഠിച്ചു, പിന്നെ പഠിച്ചതാണ് ടൈം ഡൈവേഴ്സിറ്റി. ഈ നെക്സ്റ്റ് പഠിക്കാൻ പോകുന്ന സ്പേസ് ഡൈവേഴ്സിറ്റി. ഈ സ്പേസ് ഡൈവേഴ്സിറ്റിനെ ആന്റിന ഡൈവേഴ്സിറ്റി എന്ന് കൂടി പറയും. സ്പേസ് ഡൈവേഴ്സിറ്റി ഓർ സ്പേഷ്യൽ ഡൈവേഴ്സിറ്റി. ഈ സ്പേസ് ഡൈവേഴ്സിറ്റി മെയിൻലി ആന്റിന ഡൈവേഴ്സിറ്റി എന്നും കൂടി പറയും. സ്പേസ് ഡൈവേഴ്സിറ്റി is also known as antenna diversity. So here multiple transmit and receive antenna or both are used with the spacing between adjacent antenna being chosen so as to ensure independence of possible fading event. So here either we use multiple transmit antenna, ഒന്നിൽ കൂടുതൽ ട്രാൻസ്മിറ്റ് ആന്റിന യൂസ് ചെയ്യും, അല്ലെങ്കിൽ ഒന്നിൽ കൂടുതൽ റിസീവ് ആന്റിന യൂസ് ചെയ്യും, or both, that is multiple transmit antenna and multiple receive antenna, and the spacing between this adjacent antenna is chosen in such a way that they have independence of possible fading event in the channel. അതായത് ഒരു ചാനലിലൂടെ ഒരു ചാനലിൽ കമ്പയർ ചെയ്യുമ്പോൾ വേറൊരു ചാനലിൽ അവിടെ ഇൻഡിപെൻഡന്റ് ഫേഡിങ് എഫക്റ്റ് ആയിരിക്കണം. ആ ഒരു ബേസിസിലാണ് ഇവിടെ ആന്റിന സ്പേസിംഗ് അഡ്ജസ്റ്റ് ചെയ്തിട്ടുള്ളത്. സോ ഹിയർ മൾട്ടിപ്പിൾ ആന്റിന, multiple transmit and receive antenna or both are used with the spacing between adjacent antenna is being chosen so as to ensure the independence of possible fading event occurring in the channel. So that at the receiving end there may be multiple receiving antenna separated by an appreciable number of wavelength. So the receiving end il allengi receiver side il there will be multiple receiving antenna, and this receiving antenna may be separated by an appreciable number of wavelength. The appreciable number of wavelength separation will be in the multiple receiving antennas. And the rule is to use 2 transmit antenna or 2 receive antenna, but never 2 of each. And space and diversity antenna diversity the rule nu parnayna either we can use 2 transmit antenna or we can use 2 receive antenna, but never 2 of each. And when space diversity is used, it is important that electrical distance from the transmitter to each of its antenna and to the receiver from each of its antenna is an equal multiple of wavelength long. So in space diversity le an important condition nu vechal electrical distance from the transmitter of its antenna and to the receiver of its each antenna is equal multiple of wavelength ആയിരിക്കണം, equal multiple of wavelength. And this is to ensure that when 2 or more signals of same frequency arrive at the input to a receiver, they are in phase ആയിരിക്കണം and additive. Out of phase ആയിപ്പോയാൽ cancel ആവും. So ഈ in phase nature and additive nature ensure ചെയ്യാൻ വേണ്ടിയിട്ടാണ് what we do is when the spacing is important, that is space diversity is used, it is important that electrical distance from the transmitter of each of its antenna and to the receiver from each of its antenna is an equal multiple of wavelength long. So spacing between diversity അല്ലെങ്കിൽ spacing between this antenna എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ അല്ലെങ്കിൽ ട്രാൻസ്മിറ്ററും റിസീവറും തമ്മിലുള്ള ഡിഫറൻസ് എന്ന് പറഞ്ഞാൽ it should be an equal multiple of wavelength long ആയിരിക്കണം. By ensuring this we can say that they are in phase and additive. So this is to ensure that when 2 or more signals of same frequency arrive at the input of the receiver, same frequency la രണ്ടോ ഒന്നോ രണ്ടോ സിഗ്നൽസ് വരുവാണെങ്കിൽ റിസീവർ സൈഡിൽ വരുവാണെങ്കിൽ ആ വരുന്ന സിഗ്നൽസ് എല്ലാം ഇൻ ഫേസ് ആയിരിക്കണം, എഡിറ്റീവ് ആയിരിക്കണം. സോ ഇൻ ഫേസും എഡിറ്റീവും ആവാൻ വേണ്ടി വാട്ട് വി ഡു ഈസ് ആന്റിനയുടെ ഈക്വൽ മൾട്ടിപ്പിൾ ഓഫ് വേവ് ലെങ്ത് ലോങ് ആയിരിക്കണം. റിസീവിംഗ് ആന്റിനയിലും ട്രാൻസ്മിറ്റിംഗ് ആന്റിനയിലും ദർ ഷുഡ് ബി ഈക്വൽ മൾട്ടിപ്പിൾ ഓഫ് വേവ് ലെങ്ത് ലോങ് ആയിരിക്കണം. ആൻഡ് ഇഫ് ദേ ആർ ഔട്ട് ഓഫ് ഫേസ്, ഇനിയിപ്പം റിസീവിംഗ് ആന്റിനയിൽ എത്തുന്നത് ഔട്ട് ഓഫ് ഫേസ് ആണെങ്കിൽ ദേ വിൽ ക്യാൻസൽ ഈച്ച് അതർ ആൻഡ് റിസൾട്ട് ഇൻ ലെസ് റിസീവ്ഡ് സിഗ്നൽ. So they should be in phase and additive ആയിരിക്കണം. If they are out of phase means they will cancel each other and result in less received signal. And less received signal power than if one single antenna or one single antenna system were used. So space diversity compared to this frequency diversity, this is more expensive because of additional antenna and waveguide. So here, number frequency diversity point one antenna was used. In frequency diversity, one antenna was used, but in space diversity, multiple antenna, either multiple transmit antenna or multiple receive antennas are used. So here, this is a little bit expensive compared to the frequency diversity. And this is because of the additional antenna and the waveguide which is used in this space diversity. However, the space diversity provides efficient frequency spectrum usage and greater protection than frequency diversity. Although it's expensive, but it provides greater or efficient frequency spectrum usage and greater protection than frequency diversity. So here we can see one figure. Here we have a transmitter having an antenna and a receiver having an antenna. So this configuration is a single input and single output configuration, that is SISO, SISO. Here we have a transmitter. Here that is we have a transmitter have an antenna and receiver also have an antenna, single antenna. So this is a single input, single output system. And here in the second configuration we have a transmitter, and transmitter have a single antenna, and here this is a receiver, and receiver have multiple antenna, and this multiple antenna is given to a combiner. This block is a combiner block. So this transmitter side we have a single antenna, and the receiver side we have multiple antenna. So this is known as receiver diversity. This is known as receiver diversity because in the receiver we have multiple antennas which is given to a combiner and which is fed to the receiver side. So in the receiver side, if we have multiple antenna, then this is known as receiver diversity. So this is also known as SIMO, that is single input, multiple output. Single input, multiple output. And next we can see a transmitter, and the transmitter is given to a splitter, and the splitter have many antennas. So in the transmitter side we have multiple antennas, and the receiver side we have only one antenna. Receiver side we have only one antenna. So this is known as transmit diversity. If we have multiple antenna in the receiver side, this is known as receiver diversity. And if we have multiple antennas on the transmitter side, then this is known as transmit diversity. So this is also known as multiple input, single output. That is MISO. Multiple input, single output. And last one is transmit receiving diversity. Last one is transmit receiving diversity. So here transmitter have multiple antennas and receiver also have multiple antennas, and transmitter is given to a splitter, and the receiver side we have the combiner. So this is known as transmit receiving diversity, since transmitter also have multiple antenna and receiver side also have multiple antenna. So this is known as transmit receive diversity. And this is also known as multiple input, multiple output configuration. Here this is known as non-diversity. Non-diversity, the single input, single output is known as non-diversity. And this is last one is known as transmit or receiving diversity, that is multiple input, multiple output diversity. So in the space diversity is again classified into this four types. That is selection diversity, feedback diversity, maximum ratio combining diversity, and equal combining gain diversity. So space diversity it is also known as antenna diversity. So based on the antenna, we have this classification, that is SISO, SIMO, MISO, and MIMO. And space diversity is again classified, or classification of space diversity can be done like this, like selection diversity, feedback diversity, maximum ratio combining diversity, and equal gain diversity. So in selection diversity, this is the simplest diversity technique in space diversity. This is the simplest diversity technique in the space diversity. So here the main idea is that here we can see in the figure this denote the antenna, that is 1, 2, etc. up to M, and this G1, G2, Gm denote the variable gain. G1, G2, etc. denote the variable gain. It is given to a demodulator, and the demodulator output we have the output. So here we select the best signal among all the received signals from different branch at the receiving end. Here what we do is, here we select the best signal among all the signal received from the different branches at the receiving end. So from this variable gain output, what we do is we select the best signal received from different branches at the receiving end. So here, this is the selection diversity. This is the selection diversity. Here there are m demodulators. There are m demodulators or diversity branches, and each branch gain is adjusted to provide same average signal to noise ratio. Here we can see G1, G2, etc. up to Gm. So there are m diversity branches here available, and each branch gain is adjusted to provide same signal to noise ratio. Each branch gain is adjusted, that is variable gain. This branch is adjusted in such a way that each branch provide same average signal to noise ratio. And the receiver having highest signal to noise ratio is connected to the demodulator. From this variable gain, which branch will have highest signal to noise ratio, that is connected to the demodulator. There are m demodulator to provide diversity branches, and each branch gain is adjusted in such a way that they provide they provide the same average signal to noise ratio. Each branch gain is adjusted in such a way that they provide same average signal to noise ratio, and the receiver which have the highest instantaneous signal to noise ratio, or the receiver having the highest signal to noise ratio, is connected to the demodulator. In practice, the branch with the largest S plus N by N is used. The branch with the largest S plus N, signal plus noise divided by noise, is used. That is about the selection diversity. Next is the feedback diversity or scanning diversity. Here we have the next type is the feedback diversity, and this feedback diversity is also known as scanning diversity. So instead of using best of m signals, in last class, in selection diversity, we best among the m signals demodulator provide best among the m signals. So in feedback diversity, instead of providing the best of m signals, best selected in the m signals are scanned in a fixed sequence. All m signals consider m signals scanning in a fixed sequence until the one is found to be above a predetermined threshold. So here in feedback diversity, a threshold is set, and based on the threshold, we find the best signal. So instead of using the best of m signals, the m signals are scanned in a fixed sequence until the one is found to be above a predetermined threshold. When the received signals falls below the threshold, scanning process is again initiated. We receive the signal threshold in the scanning process initiated. So here we have a comparator, and the comparator is given with the preset threshold value, and the short term average is given to the comparator, and based on that scanning is done. And based on the value, scanning is done. We receive the signal, this preset threshold scanning process once again get initiated. So this feedback is very similar to selection diversity. It is very similar to selection diversity, except that instead of always using a best of m signal, the m signals are scanned in a fixed sequence until one is found to be above a predetermined threshold. And this signal is received until it falls below the threshold, and the scanning process is again initiated. And this method is very simple to implement. Only one receiver is required. So here, this process it is very simple to implement. That's the advantage, and only one receiver is required in this process. So this is about the basic form of scanning diversity or feedback diversity. Next type is maximum ratio combining type. Maximum ratio combining type. So in this, all signals from all the M branches are weighted according to the individual signal voltage to noise ratio and then summed and added. So in MRC അല്ലെങ്കിൽ maximum ratio combining എല്ലാ സിഗ്നൽസും അതായത് M branches വരുന്ന all signals are weighted according to the individual signal to noise power ratio. Here we can see the weighting G1, G2, G3, etc. up to Gm. So the all signals are from the M branches are weighted according to the individual signal to noise power ratio and then they are summed and added. Here we can see a cophase and sum, and we are summing and adding. Here this is given to a detector, and output of the detector we get the desired output. So in this method, signal from all the M branches are weighted according to the signal to voltage noise power ratio and then summed and added. Here the individual signal must be co-phased. We can see the individual signal. It is given to a co-phase and a summer. This co-phase and summer. So the individual signals must be co-phased before being added. That is, before being get summed, the individual signals from the like R1, R2, etc. up to Rm. This individual signal, gamma, gamma 1, gamma 2, etc. up to gamma m. This individual signals must be co-phased before being getting added. Thus, an individual receiver and a phasing circuit for each antenna element is required in this maximum ratio combining. Then this maximum ratio combining produce an output signal to noise ratio which is equal to the sum of individual signal to noise ratio. This maximum ratio combining, what it do is it produces an output and which have a signal to noise ratio which is equal to the sum of individual signal to noise ratio. So this what we say, this MRC or maximum ratio combiner has an advantages of producing an output with an acceptable signal to noise ratio even when none of the individual signals are themselves acceptable. So this is one of the advantages of this MRC. So basically MRC we consider all the branches, but in a rate they are weighted according to the individual signal to signal voltage to noise power ratio, and they are summed and they are added. So before being get summed, they must be co-phased. All the signals from the branches are co-phased before being get summed or before being get added. So this is MRC, that is maximum ratio combining. And next is equal gain combining. Equal gain combining, in this method, all branch weights are set to unify. Here we are unifying all branch weight. Equal gain on combining. Here നമ്മൾ weighting factor കൊടുത്തിട്ട് വെയിറ്റ് ചെയ്യുന്നുണ്ട്. നമ്മൾ ഇനി നെക്സ്റ്റ് ഈക്വൽ ഗെയിനിങ് കമ്പൈനിങ് all branch weights are set to unity or all branch weights are unified, but the signal from the each branches are co-phased to provide equal gain combining diversity. Still അത് branch weights ഒക്കെ യൂണിഫൈ ചെയ്യുന്നുണ്ടൊക്കെ കൂടി ആ ബ്രാഞ്ചിൽ വരുന്ന എല്ലാ സിഗ്നൽസും co-phase ചെയ്യുന്നുണ്ട്. Co-phased to provide equal gain combining diversity. To provide equal gain combining diversity. So first നമ്മൾ frequency diversity പഠിച്ചു. Frequency diversity പഠിച്ചിട്ട് time diversity പറഞ്ഞു. Time diversity കഴിഞ്ഞിട്ട് space diversity പറഞ്ഞു. Space diversity യിൽ 4 type of configuration നമ്മൾ കണ്ടു. First one പറയുന്നത് non diversity, second receiver diversity, third transmit diversity, and fourth one is transmit receiving diversity. And these are the 4 classification which we have studied. That is classification of space diversity, selection diversity ennu parayum, allengil frequency diversity, selection diversity ennu parayum, and next is feedback diversity allengil scanning diversity ennu parayum. Next is MRC, that is maximum ratio combining. ഈ MRC എന്ന് പറയുന്നത് ഈ സെലക്ഷൻ ഡൈവേഴ്സിറ്റി എന്ന് പറഞ്ഞാൽ നമ്മൾ ബെസ്റ്റ് ഓഫ് M സിഗ്നൽസ് ആണ് അവിടെ കൺസിഡർ ചെയ്യുന്നത്. ഫീഡ്ബാക്ക് ഡൈവേഴ്സിറ്റിയിൽ നമ്മൾ സ്കാനിങ് വഴിയാണ് നമ്മൾ M സിഗ്നൽസിനെയും കണ്ടിന്യൂസ്ലി റിപ്പീറ്റഡ് ഒരു ഫിക്സ്ഡ് പാറ്റേണിൽ സ്കാൻ ചെയ്തിട്ട് വി സെലക്ട് ദ ബെസ്റ്റ് സിഗ്നൽ. അല്ലെങ്കിൽ ബേസ്ഡ് ഓൺ എ ത്രെഷോൾഡ്, നമ്മൾ ത്രെഷോൾഡ് സെറ്റ് ചെയ്തിട്ട് ആ ത്രെഷോൾഡിനെക്കാട്ടി മുകളിലുള്ള സിഗ്നലിനെ സെലക്ട് ചെയ്യും. And when the received signal thresholdനെക്കാട്ടിയും താഴെയാണെങ്കിൽ if it falls below the threshold, once again scanning process initiate ചെയ്യും. MRCയിൽ നമ്മളൊരു വെയിറ്റിംഗ് ഫാക്ടറിനെ ബേസ് ചെയ്തിട്ടാണ് ചെയ്യുന്നത് വെയിറ്റിംഗ് ഫാക്ടറിന്റെ വരുന്ന ഔട്ട്പുട്ട് വരുന്ന സിഗ്നൽസ് നമ്മൾ കോപ്പീസ് ചെയ്യും, എന്നിട്ട് നമ്മൾ ആഡ് ചെയ്യും. ആൻഡ് ഈക്വൽ ഗെയിൻ ഡൈവേഴ്സിറ്റിയിൽ നമ്മൾ ഈക്വൽ വെയിറ്റ് ആണ്, അത് നമ്മൾ വെയിറ്റിംഗ് ഫാക്ടർ ഇറ്റ് ഇസ് യൂണിഫൈ ചെയ്യും. വെയിറ്റിംഗ് ഫാക്ടർ ഇസ് or weighting factor is unified. It is equal gain combining. And next ആണ് selection diverse. These are the categories, the classification. There is selection diversity, feedback diversity, and this is MRC, that is maximum ratio combining, and this is equal gain combining. Next we are going to study about the receiver, that is rake receiver. The rake receiver we mentioned the time diversity in the case. So this is a radio receiver designed to overcome the effect of multipath fading. So this rake receiver multipath fading in the effect overcome design receiver. So it uses several correlators assigned to each multipath component. Oro multipath component it uses several correlators. That's rake receiver first part. That oro multipath, for each multipath component it uses several correlators. So this rake receiver basically just in the first order that multipath fading effect overcome use the receiver. Design the receiver rake receiver. And it uses several correlators assigned to each multipath component. So each correlator is independently decode signal multipath component. So ഓരോ കോറിലേറ്ററും ഇൻഡിപെൻഡന്റ്ലി ആണ് ഡിക്കോഡ് ചെയ്യുന്നത്. ഓരോ സിംഗിൾ മൾട്ടിപാത്ത് കോമ്പോണന്റ്സും ഓരോ കോറിലേറ്ററും ഇൻഡിപെൻഡന്റ് ഓഫ് അതർ കോറിലേറ്റേഴ്സ് ആണ് ഡിക്കോഡ് ചെയ്യുന്നത്. ആൻഡ് ദ ഔട്ട്പുട്ട് ഓഫ് ഈച്ച് കോറിലേറ്റർ ഇസ് വെയ്റ്റഡ് ടു പ്രൊവൈഡ് ബെറ്റർ എസ്റ്റിമേറ്റ് ഓഫ് ട്രാൻസ്മിറ്റ് സിഗ്നൽ. സോ ഈ കോറിലേറ്ററിന് വരുന്ന ഔട്ട്പുട്ട് എന്താ ചെയ്യുക വെച്ചാൽ ഇറ്റ് ഈസ് അഗൈൻ ഗിവൺ എ വെയ്റ്റഡ് ഓർ അതിനൊരു വെയിറ്റ് കൊടുക്കും. Correlator output is weighted to provide better estimate of transmitted signal. Transmit ചെയ്യുന്ന സിഗ്നലിന് better estimate കിട്ടാൻ വേണ്ടി നമ്മൾ ഈ കോറിലേറ്ററിന്റെ ഔട്ട്പുട്ട് നമ്മൾ ഒരു വെയിറ്റിംഗ് ഫാക്ടർ വെച്ചിട്ട് വെയിറ്റ് ചെയ്യും. And the demodulator and decision are based on the output of the correlator. That is demodulator and decisions are based on the output of the correlator. There are several sub-receivers and the sub-receivers നമ്മൾ fingers എന്ന് പറയാം. The sub-receivers correlator branch sub-receiver. So there are several sub-receivers and the sub-receivers are called fingers, and these fingers are used in rake receiver. Fingers it's correlators. So there are several sub-receivers and the sub-receivers are called fingers and they are used in this rake receiver. So the rake receiver attempt to collect the time shifted version of original signal. So time diversity in the case. So this rake receiver attempt to collect. Rake receiver time diversity use in the category of CDMS spread spectrum use. So this rake receiver it attempt to collect the time shifted version of original signal by providing a separate correlation receiver for each of the multipath component. ഓരോ മൾട്ടിപാത്ത് സിഗ്നൽസിനും അല്ലെങ്കിൽ ഓരോ മൾട്ടിപാത്ത് കോമ്പോണന്റിനും ഒരു സെപ്പറേറ്റ് കോറിലേഷൻ റിസീവർ പ്രൊവൈഡ് ചെയ്തിട്ട് they try to or they attempt to collect the time shifted version of original signal. And this rake receiver is designed for CDMA, code division multiple access. The rake receiver is designed for code division multiple access and it equalizes the effect of multipath. Problem and the spread out individual echo signals of multipath. It spread out the individual echo signal of the multipath and each signal is delayed according to the peak found in the received signal. Normally rake receiver in phase avamandi each signal is delayed according to the peak found in the received signal. So this is the block diagram for a rake receiver. Here we can see R of t. It is a received signal and it is given to M correlators, correlator 1, correlator 2, correlator 3, etc. up to correlator M, and output of this correlator is Z1, Z2, Z3, etc. up to Z. This is given to a weighting factor. We can see alpha 1, alpha 2, alpha 3, etc. up to alpha M, which is then sum, and the output of the summer is Z dash, and it is given to an integrator, which is nothing but a demodulator, that is 0 to T dt, and the output of the demodulator is Z, which is given to a decision device or a decision device which is designed whether it is greater than or less than a defined preset or threshold value, and the output of the decision device we get m dash of t, which is an estimate of original signal. So each correlator here independently decodes the single multipath component, and the output of each correlator is weighted to provide better estimate of transmitted signal. So at the decision device output, we get the better estimate of transmitted signal. That is m dash of t. M of t are transmitting the signal angle. At the output of this rake receiver, we get m dash of t, which is a better estimate of transmitted signal. So ഇവിടെ ഓരോ മൾട്ടിപാത്ത് കോമ്പോണന്റും നമ്മൾ ഡിഫറെന്റ് കോറിലേറ്റേഴ്സിലേക്ക് പ്രൊവൈഡ് ചെയ്യും. ഈ ഡിഫറെന്റ് കോറിലേറ്റേഴ്സ് ഇൻഡിപെൻഡന്റ്ലി ആണ് കോറിലേഷൻ പെർഫോം ചെയ്യുന്നത്. This correlator 2 does not depend upon any correlator 3. ഓരോ കോറിലേറ്റേഴ്സും perform independently. That is, each correlator independently decodes signal multipath component, and the output of each correlator is weighted to provide better estimate of transmitted signal. And the demodulation and the decision are based on the output of correlator. The demodulation and decision is based on the output of correlator. So this figure shows the M branch rake receiver. Oro branch, that is correlator 1, correlator 2, correlator 3, that is Z1 output to the branch, Z2, Z3, Z4, Z etc. is called as fingers. Fingers this are the sub receivers. These sub receivers are also called as fingers. The sub receiver are also called as fingers. And here this is a M branch rake receiver. Rake receiver, and we have Z dash. Z dash is summation m equal to 1 to m alpha m into Zm. This alpha m is the weighting factor. This Zm is the output of correlator. And this equation for this alpha m is equal to Zm square divided by summation m equal to 1 to m Zm square. This is the equation for this weighting factor Zm. Zm is equal to alpha m is equal to Zm square divided by summation m equal to 1 to m Zm square. So this is basically about rake receiver. So rake receiver is designed for the CDMA, that is core division multiple access. And here it is a radio receiver. Basically, it's a radio receiver, and it is designed to overcome the effect of multipath fading. And it uses the several correlators assigned to each multipath component. And each correlator is independently decode a single multipath component. And the output of each correlator is weighted to provide a better estimate of transmitted signal. And the demodulation and decision are based on the output of correlator. Several sub-receivers, also called fingers, are used. That is, correlators are used. And rake receiver, what it do is it attempt to correct the time shifted version of original signal by providing a separate correlation receiver for each of the multipath signal. And the rake receiver is designed for CDMA. It equalizes the effect of multipath. It spread out the individual echo signal of the multipath component, and each signal is delayed according to the peak found in the received signal. And this is the block diagram of rake receiver. Here in the block diagram, the output of the summer is Z dash, which is equal to summation m equal to 1 to alpha m into Zm, and the weighting factor alpha m is given by Zm square divided by summation m equal to 1 to Zm square.